call is now being recorded.
So I'll start and let the students come join later. In today's class, we are going to see vector grouping of transformer, which is essential for parallel operation, and some problems in the previous titles, like EMF equation and the equivalent circuit of transformer, and one more problem based on calculating efficiency and percentage regulation. Okay. So these are the topics we covered in the last classes. And we derived, with this we solved in the last session. Okay. So we derived an equation for amount of load shared by two transformers. Okay. So this is the final equation. How much amount of power is shared by two different transformers connected in parallel. Okay. And next is the vector grouping. Since it is in first module, I didn't cover this. The reason is vector grouping can be studied only after studying about the various types of connections of transformer. We know that transformer has different connections like star to star, star delta, delta delta, and delta star. So these are the various combinations of star connection and delta connection. Look at this diagram. The first one is star connected. Look at this. Out of 6 terminals, 3 terminals have been connected at a common point. Isn't it visible? So this common point can be denoted as neutral. Okay, that is C1, B1, and A1. All these 3 terminals have been connected at this common point. And C2, B2, A2. These 3 terminals have been left for connecting source or the load. We can connect either source or load. Okay, this is one type of connection in star. Okay, so the second possibility is keeping the terminals denoted 1, C1, B1, A1 for connecting the terminal external sources like source or load. So we can either connect a source or load here. And these 3 terminals, C2, B2, A2, these 3 are connected in neutral point. Okay, this is second type of star connection. Only these 2 possibilities are available in star connection. So either we can connect C1 terminals, 1 terminal, or 2 terminals. Okay, and this dot indicates, what is the meaning of a dot? You would have studied this in electronic circuits and electrical circuits. What is meant by dot? What is the meaning of that dot? So that indicates either the current is entering the point or leaving the point. Okay, so it is an indication of current direction. So let us assume it is at C2 here. Okay. Similarly, this one is delta connected. We have 4 combinations of delta connection. I'll explain these combinations first, then we will move to the vector grouping. So totally we have 4 combinations. This is what usually we will do. So C2, C1, B2, B1, A2, A1. These 3 windings we are having. Okay, so one winding will be having 2 terminals. Look at A phase. So this A phase winding is having 2 terminals named A1 and A2. Okay, and this is phase B, so which is having 2 terminals one is B1 and the another one is B2. This is C terminal, which is having two terminals, C1 and C2. Okay. So in delta connection, one terminal of a phase is connected with other terminal. Look at this. So one terminal is connected with other terminal, and the other terminal is connected with third phase. Do you understand? So C2 is connected with B phase, C1 is connected with A phase. So this is how delta connection is done. Similarly, we can make four different combinations in this manner. For connecting in delta, the two terminals of a single phase winding should be connected with two different phases. Okay, that is the condition. Okay, and out of that condition, we are creating four different possibilities of delta connection. Here, C2, B2 and A2, these terminals have been left for external connection. But look at here, C1, B1 and A1, these three terminals have been left for external connection. Okay, external connection in the sense, a transformer, a three-phase winding will be having 6 terminals totally. Okay, if it is a three-phase winding, it will be having 6 terminals. Out of this 6 terminals, 3 will be interconnected, will be connected themselves in the phase windings itself. The next 3 terminals will be connected either in source side or in the load side. So we have 2 combinations in a star-to-star connection, isn't it? In primary side, we will be connecting in star manner. In secondary side, we will be connecting in star manner for a star-to-star connection. Okay, so totally we will have 6 external terminals to connect the source and the load. Okay, so how we will connect? What is the relationship between the polarity? Those things are dealt in vector grouping. Vector grouping is explaining all these details. Okay, how these 2 windings are coupled. What is happening to the polarity of current? What is happening to the EMF induced in the polarity of EMF induced in the phase winding? So those details can be studied with the help of vector grouping. Okay. And look at the third combination. The difference between first and second combination. Look at this. Can anyone tell me? So here also C2, B2 and A2. These 3 terminals are left for external. C1, B1, A1. These 3 terminals have been connected internally. Okay. So what is the difference between these 2? Here also C2 terminal, B2 terminal and A2 terminal have been left for external connection. Here also we are using the same C2, B2 and A2. But we have a difference in winding connection. Look at this. In this one, C1 terminal is connected with B2. In the 5th diagram, lower middle diagram, C1 is connected with B2 terminal and B1 is connected with A2 terminal. But look at here, C1 is connected with A2, B1 is connected with C2. So we need to be very clear while drawing this diagram. This may make you confused. Drawing these 2 are easy. So drawing the star connection is very simple. Either we will be keeping the 2 terminals, second terminals for the external connection, and these 3 have been connected internally. So drawing a star connection is very simple, but delta connection will make confused a little bit. Yes, very good. Hariharan has answered it correctly. And look at the comparison between these 2 terminals, 2 types of windings. So here also C1, B1 and A1. These terminals have been left for external connection. C2, B2, A2 have been connected internally. The same terminals have been connected internally, but look at the connection difference between them. Between C2 and B2, we have one phase. Between these two phases, sorry, these two terminals, between C2 and B2, we have B phase, isn't it? But look at here, between C2 and B2, what is the terminal we have? C2 to B2. So we have here C terminal. So we may assume this is also reverse of this. Okay. So these two diagrams are replica of them, vice versa connected, and these two have been connected inversely. Okay. Similarly, these two are inversely connected. So with the help of these 6 structures, we can make this much amount of connections. I'll explain what is 0, 6, 1, 5, 7 and 11. So these details I'll explain later. First we have to mention this part. Okay, look at this. 3-phase connection. What are the possible connections? We have one capital letter, Y is mentioned in uppercase, and one side, the left, in the right hand side, Y is mentioned in lowercase. Okay, it means in left side, that is maybe a source side, the voltage will be high. If you put that in capital letters, it means high voltage winding. Okay, and then star connector, and in the second side, we have low voltage winding, which is denoted with small letter L. Low voltage winding. LV stands for low voltage. Okay, so it means Y means star to star connection diagram. Star to star. This is star to star combination. Okay, so capital Y stands for high voltage winding, small winding stands for small y stands for low voltage winding. Okay, so in the primary side we have high voltage, in the secondary side we have low voltage winding. Okay, similarly, what is this? D stands for delta and small y stands for star connection. So this combination must be delta to star connection. And the third one is star to delta connection. So in this diagram, star connection is high voltage winding, delta connected is low voltage winding. Similarly, the fourth one is delta to delta. In the primary side we have high voltage, in the secondary side we have low voltage. So both of them are delta connected. So these four, with the help with these 4 combinations, we can make this much of combination using this diagram. So I'll explain what is these terms are standing for. So before going to that, we should know what is vector grouping. Look at the first sentence. So vector grouping is the one which explains what is the relationship between the primary winding and secondary winding. What is the phase sequence of primary winding and secondary winding. Also, what is the polarity of current passing from induced EMF. Okay, due to the induced EMF, what is the current polarity? So those details we can identify with the vector grouping. Okay, this is the purpose of drawing vector grouping. So the first diagram is called as y0. Look at this point. So y0 stands for star to star connected, and this one is called as clock, 0 clock, or it is called as 12 o'clock. So why it is called as 0 o'clock or 12 o'clock is, where will be the needle of second needle and hour needle in a clock at 12 o'clock? At 12 o'clock, the hour needle and second needle, so minute needle, both of them will be in. So this is the blue color is minute needle, red color is hour needle. So these two will be at same point at 12 o'clock, isn't it? So with this explanation, they have explained these values. So these are explaining about time period. 0 stands for 0 o'clock or 12 o'clock. 6 is 6 o'clock. At 6 o'clock, the hour needle and minute needle will be exactly opposite to each other. So how it will look like is, so the minute needle will be at 12 and hour needle will be at 6. Okay, so if you draw a clock, so this will be the case. Minute needle will be at 12, hour needle will be at 6. Okay, at 5 o'clock, what will be the direction? At 5 o'clock, in all the cases, minute needle will be at 12. Okay, so this is the minute needle. At 5 o'clock, this will be at here. The hour needle will be at here. What is the angle covered? So assume the total is 360 degrees. When the time is 1 o'clock, the angle will be 30 degrees. Okay. When the time is 2 o'clock, the angle will be 60 degrees. At 3 o'clock, the angle will be 90 degrees, and at 4 o'clock, the angle will be 120 degrees, and at 5 o'clock, the angle will be 150 degrees each other. Okay. So what is the angle at 6 o'clock? The hour needle and minute needle will be 180 degrees delayed with each other. Okay, here assume the hour needle has high voltage windings, EMF, polarity of high voltage winding, and minute needle at low voltage winding, EMF. I will explain that later. Okay, you don't get confused. The reason for putting this one is 0 o'clock or 6 o'clock is, at 0 o'clock, both of them, the minute needle and hour needle, will be in phase, in a same polarity, in this angle. Okay. At 6 o'clock, they will be out of phase. Minute needle will be at this position. Hour needle will be at this position. So they will be exactly connected in opposite polarity. Okay. So while explaining about parallel operation of a transformer, I would have told you there are several conditions for connecting two transformers in parallel. What are the conditions? Let us go through that again. So look at this. Same voltage ratio of transformer. Identifying the same voltage ratio is very easy. Okay. So we can easily identify. We can use meters, instruments for finding out the voltage. And if you want to make any correction, for example, assume we are going to connect 440 volts transformer secondary with 400 volts transformer secondary. Okay. The first transformer secondary voltage is 400. second transformer's voltage is 440, 400 and 440. So we need to combine these two transformers. Okay, this is what the project have been given to you. Okay, what will you do to make them coupled? And we have to follow this condition. The voltage ratio must be same. What will you do? The first transformer is having lesser voltage compared to second transformer, isn't it? We'll write that so that you can understand. Transformer 1, secondary voltage is 400. Transformer 2, secondary voltage is 440. What I need to do is, I need to couple these two transformers without any problem and following the condition of parallel operation. So I need to connect these two transformers. The first condition is violated here. The reason is the voltage of these two transformers are not same. So what should I do is, I need to increase the number of turns in the secondary of the transformer. Okay, so what will happen when you increase the number of turns, coil turns in the secondary side? So based on number of turns, the EMF will be increased, isn't it? The induced EMF will increase and current will fall down. So that is what the condition we have studied till now. Okay, so when I increase the number of turns, when I adjust the number of turns of secondary of the first transformer, this voltage will gradually increase to 440. So this first condition can be satisfied easily by some mechanical arrangement. Okay, so by adjusting the number of turns, we can easily adjust the voltage which we require to couple two transformers. Okay, and the impedance is also based on selection of coil winding. Okay, but the problem arises at this point, same polarity. This we cannot identify easily. We have to perform polarity test to identify where the EMF induced and where the current polarity, and those details we have to identify one by one or by conducting the test. So this vector grouping is helping us to find the polarity of current flowing through two transformers. Okay, when they are connected in parallel. Okay, so this is the first point we need to look at. Vector group of a transformer is essential property for successful parallel operation of two transformers or two or more transformers. Okay, so we have a testing for vector grouping as well. So either they are connected in 0 o'clock or 12 o'clock. Those notations, 12 o'clock or 6 o'clock means they are connected in phase or they are connected out of phase. So that is the detail they are telling. Okay. So let us, I will explain you how to draw this diagram. Okay. So look at the first one. We have two star-to-star connected transformers. So first we are going to see YY0. What is YY0? Two transformers, star-to-star connection. That is, high voltage winding is star connected, low voltage winding is also star connected, and the phase angle between them, the induced EMF of the phase angle of induced EMF between them is 0. Okay, that means the phase angle difference is 0 means these two transformers have been connected in the same polarity. For example, we can look at this diagram. So these two are in aiding polarity. Like this, they have been connected like this. So what is the sum of voltage? So what is the total voltage across these two sources? So for example, assume this is 6 volts and this is 6 volts. So what is the total voltage? If I put a voltmeter across these two batteries, what is the total voltage I will get? Can anyone pose the answer for this? Two voltage sources or two batteries have been connected one after another. So the total voltage will be sum of these two, which is 12 volts. Isn't it? The voltmeter will show you 12 volts reading. Okay. Similarly, So this combination y0 is the same as this combination. Okay. So what is happening here? I'll explain how do we call this as 0 degrees? I'll tell you. Okay. First, we have to draw the vector diagram. So this one is very important. How to draw this? We should know this. Okay. So look at here. I told you every phase winding will be having two terminals. One is denoted as R1. The second terminal is denoted as R2. Okay. Similarly, Y phase will be having two terminals, Y1, and second terminal will be having Y2. And similarly, V1 and V2. Okay. So I have R1 here, Y1 here, and B1 here. So what are internally connected? R2, the terminal R2, Y2 and B2. These three terminals have been connected at a common point. So what I'm going to do is, I'm going to make them connected in a common point like this. Okay. So this is my R2 terminal and this is Y2 terminal and this is B2 terminal. So they have been connected at a common point. So this is the vector diagram for this. Okay. So if I want to find out R phase alone, it will be between R1 and R2. Look at this. The R phase. This is the phase winding. The black color dark square is rectangular R phase winding. Okay. So the phase winding is lying between R1 and R2 in this direction. So I'm taking this as minute needle in the clock. Okay. So assume this as minute needle. Okay. In primary side, I have connected the minute needle. So primary side is assumed as minute needle. Okay. In the clock. Okay. Look at the same diagram. So similarly, this is denoted with small letters, small r, small y. In lower cases, lowercase r, y, and b. Okay. Similarly, they will also be having the same polarity and same winding number. R1 here, Y1 here, and Y2 here. The first B1 here. Okay, the first combination, what we are looking at is both of them are at 0 degree phase shifting. Okay, so what are the commonly connected terminals? R2, Y2, and B2. So these three terminals have been connected in a common point. Okay, draw the same diagram for them. So R1 is here, R2 is here. Similarly, Y1 is here and Y2 is here as well. B1 is left for open connection and B2 is left for is connected at neutral point. Okay. So by seeing these two diagrams, we can identify this diagram is replica of this diagram without any shifting. So R1 is there, R1 is here. B1 is here, B1 is here. Y1 is here and Y1 is here. Okay. So if I want to find out R phase, this part, R phase winding, I will draw a vector in this direction. Okay, which is same as that of this one. Okay, so these two are similar, or these two are in phase with each other. Okay. So the hour needle was in this direction, sorry, minute needle was in this direction, and hour needle also was in this direction. So what is the time period when hour needle and minute needle are in the same position? Okay, so these two are in exact this vector, so the time will be now 12 o'clock. That is what is denoted as 0 o'clock. Okay, so in the clock, if you draw that in a clock, minute needle will be here as well as the hour needle. So both of them are same phase at 12 o'clock. So explaining them with comparing them with the clock is just to indicate in what is the phase shifting between these two. Okay, for a three-phase system, the phase angle difference between each phase will be 120 degrees. Okay, that you know very well. So when you combine all these three, you will be getting a 360 direction, 360 polarity current flow. Okay, so similarly in a clock, if you assume that one rotation takes 360 degree, isn't it? So this is also will cover 360 degree. That is the reason why we are comparing the phase angle difference with a clock. Okay, so the second diagram, look at this. So if you understand this, you will find out why these numbers have been given here. So Y to Y, you know that it is a star to star connection. D, you know, it is delta to delta connection. So what is this number is indicating? That is what we are studying now. So first we have seen what is Y0. Okay, now we will see Y6. In the first diagram, I told you, so this is R1 and this is R2, sorry, this is Y1 and this is V1. Okay, here assume this is R2, the terminal has been reversed, R2, and this is Y2 and this is B2. This diagram is same as that of this combination. Okay, so in star we will get two different combinations like this. So for first diagram I showed you how this is connected. In second diagram, the external terminal connection is inverse. Okay, that this is the inverse of this one. Okay, for that we are going to draw the vector diagram. Okay. So initially it was R1, Y1, B1. Now this is kept as R1, R2, R3, and sorry, R1, Y1, B1. The external terminals initially connected was R1, small y1. Now the external connecting terminals are Y2, R2, and B2. Compare these two. Between R1 and R2 we were having R phase, but here it is inversing. So the external the coil is connected inversely. So the vector diagram will be like this. So look at this diagram. The R phase was in this direction. Here the small R phase is in this direction, from this to this. Okay, so reaching the neutral, we are drawing like this. For reaching the neutral, that we are drawing from lower to upper. Okay. So this will look like the minute needle will be in this phase and our needle will be in opposite phase. Okay. So the total phase between these two is 180 degrees. Since the winding is inversely connected, the phase will be shifting 180 degrees. Okay, that is what we have drawn here. Okay, the phase angle between these two is 180 degrees. So it is called as 6 o'clock. Why 6 o'clock? Okay, so in the same way, delta connection is also drawn. Delta connection does not have any neutral point. We know that very well. Okay, there is no common point of coupling connection. But in this diagram, I have made a virtual neutral point that is drawn in this axis. So this is assumed to be a neutral. There will be no neutral point, but it is assumed virtually a neutral point. Okay. So this is an assumption. You don't need to draw even this. Okay. So for explaining the vector diagram, you need to draw this. That is very important. Okay. So I'll explain this with the numbers. So this is initially R1, Y1, B1. And this is R2, Y2, B2. The same notation is used here. R1 is left for external connection, Y1 is left for external connection, and B1, RYB1 are left for external winding, external connections, either source or load. Okay. R2 is connected with Y1, Y2 is connected with B1, B2 is connected with R1. So these two diagrams are same, isn't it? In the primary side as well as secondary side, between R2 and Y2, we have Y phase. Between R2 and Y2, we have Y phase. Between Y2 and B2, we have B phase. Look at this, between Y2 is here, B2 is here. So between these two notations, we have B phase. Okay, similarly, between B2 terminal and R2 terminal, we have R phase. The same is followed here. R2, between R2 and Y2, we have Y phase. Between Y2 and B2, we have B phase. Between B2 and R2, we have R phase. Okay. So both of them looking similar. So the phase difference between these two will be 0. Okay. That is why it is denoted as delta to delta 0 clock. Okay. So what happens if this is reversed? Okay. So look at this diagram. The second diagram, the secondary side, it differs. Look at this combination. R2 is connected with Y1. But look at here. R1, R2. So this diagram is reversed. We just explained with this diagram. So compare these two. Between C2 and B2, we were having B phase. C2 and B2. Between B2 and C2, we have this phase. Between B2 and A2, we were having this phase. And between A2 and C2, we were having C phase. Okay, this is what the first diagram, this diagram. Okay. And this one is replica, inverse of this. Between C2 and B2, what is the phase we are having? Okay, it is reversing, isn't it? So what is happening here is we will get 180 degree opposite polarity. Okay, that is why it has been drawn as DD6. That means the minute and hour needles will be out of phase with each other. The angle between them will be 180 degrees. So in such a way, we can create this much combination. So either star to star connection is connected in 0 degrees or 180 degrees. Multiply this numbers with 30. Okay. So 0 into 30 is 0. 6 into 30 is 180 degrees. Either you can connect the star to star connection with a phase difference of 0 degrees, or you can connect the star to star connection with a phase difference of 180 degrees. Okay. And here, either you can connect delta to star connection with 30 degree phase shifting, or 150 degree phase shifting, or 210 degree phase shifting, or 330 degree phase shifting. Okay, do you understand what I'm telling? So in a similar way, you can make this much combination, and while writing in examination, you just explain with just two vector grouping, either this one. So this one will be easy to draw, YY0, YY6. So draw this and explain. You can easily score marks. Okay, so if it is given for a 6-mark question, you just draw these two diagrams and don't forget to draw this table, write this table. Okay, this is very important. What are the possible combinations in a 3-phase circuit? Okay, do you understand? So next, so with this vector grouping is over, we have one more topic pending in the first part of second module, which is off-load and on-load tap changing transformer and AC voltage regulator. Okay, so these are more or less equal to an auto transformer. So for that, let us once again go through what is auto transformer. I'm not going to teach you what is off-load and on-load tap changing transformer now. We will see that in the next class. Now we are going to derive some problems. But I'll give you introduction about a tap changing transformer. Okay. So in a practical auto transformer, some tapping will be provided like this. Look at this. So tappings have been provided like this. Using a knob which is kept on the auto transformer, we have to rotate it manually. Okay. So while rotating, what is happening is we will be having a contactor. Okay. So that contactor will touch these tappings. If the tapping is kept at this point, for example, if the contactor is at this point, the secondary side, the load side, we have only this much winding. Okay, only this much winding is connected in the secondary side. So I told you in many classes, V2 is directly proportional to N2. So based on number of turns, induced EMF will be there. Okay, when number of turns is very less, the secondary will be receiving very less induced EMF. Okay, so when I put that at here, so now this is moved to here. Now the contactor is at this point. I'll get more number of windings compared to the first case. Okay, so now I'm getting some coil greater than so now the number of turns in the secondary is increased. What will happen is V2 will increase, this voltage will increase. So similarly, so this is the working of an auto transformer. Similarly, in a high power distributed transformer, due to some power failures or load variation, the voltage requirement will vary in phase to phase. Okay, some phase, for example, if it is, we will be having three-phase distributed system. Okay, and that will be separated to the houses in a single phase manner. Some houses will be receiving single phase winding, single phase supply, and some houses will be receiving three-phase supply. Okay, if this is not connected balanced, for example, three single phase connection is taken from three different houses. Okay, so first house is receiving R to neutral. Second house is receiving Y to neutral, single phase supply. Y to neutral means single phase supply. Okay, third house is receiving B to neutral, that is one single phase. Okay, so three houses have been connected in three phases. Okay, first house is shut down. There is no instrument is used in the first house. No appliance is used in the first house. But the two houses, other two houses, Y and B, they will be receiving the power in a maximum demand. Okay, so what will happen now is B phase and Y phase current will be passing in B phase and Y phase, and there will be no current passing in A phase. Okay, so in power system, this problem will not arise. Assume it is a isolated power system. For example, you are generating power and you are feeding, with a single generator, you are feeding these three houses. What will happen now is, there will be unbalanced condition occur. Okay, Y and B phases will be loading, A phase will be completely shut down. Okay, at that time, what we will do is, we will use some additional transformers called tap changers. So those will help in balancing them, the unbalanced voltage. Okay, so we will study about that in the later class, next class. Now we will see some problems. Okay, so I would like to derive this. Okay, look at the screen now. When I tell you to go look at the board, you may pin the board. Okay, so read the problem or take a screenshot of this. A 3300 volts, 220 volts, 30 kVA single phase transformer takes a no load current of 1.3 ampere. Okay, they have given 4 data from this. 3300 volts bar 220 volts. Okay, and the power rating, kVA rating has been given, which is 30, and the no load current has been given, which is 1.3 ampere. Okay, iron loss component is equal to 0.3 ampere. Okay, and they are telling you to find out no load input power, magnetizing component, and no load power factor. Okay, so this is what we are going to derive now. I'll stop the screen sharing now. Look at the board. You may pin the board, my name, which is showing the board. Can you see the board now? Okay. So I want you to unmute yourself and answer for this question, since I cannot see the screen. So what are the data given? So they have given the voltage ratios V1 and V2 have been given here. What is the value of V1, which is 3300 volts, and V2 is 220 volts, isn't it? Okay. And the value has been given, is denoted as Q, is equal to 30 kVA or you can write that as 30 into 10 to the power 3 volt ampere. Okay. Next one, they have given no load current. I naught value has been given, which is 1.3 ampere, and IC value has been given, which is 0.3 amp. So these are the data given in the problem. So they have mentioned this current IC as working component or core loss component. I told you they will be giving you with a different name. Once again, I repeat that. This is called as core loss component or working component or wattful component. So you this may confuse you. No, one is IC or IW. Okay, they may give you with a different notation. Don't get confused with this. This is surely confusing you. And the second one is given with the name IM, magnetizing component or wattful component. Okay, we have different equations for this. The vector sum of these two is the no load current. Okay, in this problem they have given you and core loss component. What they are telling us to find is the data to be find is no load input power, magnetizing component. No load input power is denoted as E naught or W naught. Second one, they have to find is magnetizing current. No load condition. Third one is we need to find out no load power. Okay. So let us see what is the input power at no load condition. Input power at no load condition.
Sir, watch break out, sir.
Is it okay now? Hello?
Yes, sir. Okay, sir.
Okay. So the no load input power can be written as V naught is equal to V1 I naught cos phi naught. Okay. So look at this equation. Available from this equation is V1 is given as 3300 volts.
Repeat break also, sir.
Has been given. Yes. Do you have any doubt?
Repeat break also,
Someone is
sir.
turning on the mic.
So Nagaraj sir,
Good okay now?
so Nagaraj sir, charge கம்மியா இருக்கா ப்ளூடூத் மைக்கு?
அப்படியே தான் இருக்கிறேன். சரி, என்னோட ஹெட்ஃபோன் யூஸ் பண்ணிக்கிறேன் சார்.
ஓகே.
Can you hear my voice now? Sir, இப்போ கேக்குதுங்களா? Sir, இப்போ கேக்குதுங்களா?
எக்கோ வருது சார், எக்கோ வர மாதிரி இருக்கு. பேசுங்க சார்.
கேட்கலையே.
சார் நீங்க பேசுங்க.
கேட்கல சார். ஹலோ சார்.
இப்போ எடுங்க சார், கிளியரா தான் இருக்கு.
ஓகே சார். So in this equation, we know the value of V1, I0, and power factor value. There is no clue they have given about power factor. Okay, power factor value is not given, but indirectly they have given the core loss component. Okay, so no load current can be given with two names which are IC, two components which are IC and IM. So here IC is I0 cos phi naught and IM is I0 sin phi naught. Though they have not given the power factor, they have indirectly given the power factor by means of core loss component. Okay, so I0 cos phi naught, this entire term has been given. Okay, so what is P naught? You can easily directly calculate V1 into IC. Okay, so what is current value? IC is 0.3, V1 is 3300 into 0.3, which is, what is the value of this?
990, sir.
990 watts. Yes, very good. Don't forget to put the unit. 990 watts. So next one, we have to find out the magnetizing component. Which is IM, magnetizing component of no load current. Okay, so IM is given as I0 sin phi naught. Okay, either we can use this formula or we can go for this equation. I0 is equal to IC square plus IM square. So this, I told you, IC, the no load current, is the vector sum of core loss component and magnetizing component. So in case if it is a vector sum, we will put this equation, square root of IC square plus IM square. Okay, so IC value is I0 cos phi naught, IM value is I0 sin phi naught. When you square this, you will get cos square sin phi naught, sin square phi naught. So both of them are having I0 as common. So while taking it outside, you will get cos square phi naught plus sin square phi naught. So sum of sin square theta plus cos square theta is 1. So these two will get cancelled. You will get I0 inside. Okay. So from this equation, I can write the magnetizing component IM as I0 minus IC whole root. Can we write? So what is I0? I0 is 1.3, I think. Yes, 1.3 ampere square minus 0.3 square. What is the value? Square root of 1.3 square minus 0.3 square. Can anyone answer?
Can anyone answer for this question?
Sir, 1.26.
Yes, that is the answer. 1.26 amperes. Yes, very good. Okay. So finally, we need to find out the no load power factor. So third one, we need to find out the no load power factor, which is cos phi naught. We know IC is equal to I naught cos phi naught. So out of which we know the value of IC and I naught. So these values we know. So cos phi naught must be IC divided by I naught. Okay. So what is the value of IC? Just 0.3. I naught value is 1.3, which will give you 0. Tell me the answer.
0.23, sir.
Yes, very good. So the answer is 0.23. So this is the no load power factor. Okay. So in all the cases, you please check it down. The no load power factor will be very less. Okay, very poor. We will desire the power factor to be 1 always, but it is not possible in the practical transformer. But we will go for a 0.9 lagging or 0.8 lagging. This will be called a better power factor. So anything between 0.99 to 0.8 will be called as better power factor. But at no load condition, this is the value. Even in practical transformer, which we are having in the laboratory, we will be getting this much of power factor only. Okay, it indicates at no load condition, the machine is assumed to be a pure inductor. Okay. Let us move to the second question. I stop the camera. Now I request you to look at the screen. The second problem, please take a screenshot of this. At 20 kVA, can you see the screen now? Slide. I turned off the camera and slide sharing the. So look at the problem. A 20 kVA per 21 volts single phase 50 Hz transformer has a primary resistance of 2.5 ohms and reactance of 4.8 ohms. Okay, the primary winding details have been given. So primary winding will be having two. I'm just seeing the problem. Okay, 2 ohms and a reactance of 4.8. The secondary resistance of 0.1 ohm and 0.08.
Sir, voice is not audible, sir.
or better I'll Is it okay now? Okay. So the equivalent resistance, reactance, and impedance referred to secondary. In the first two subdivisions, they have asked the details referred to primary. In the second detail, they have asked third subdivision, they have asked the details of windings referred to secondary side, and finally they have asked you the copper loss of the transformer. Please take a screenshot of this, and we will work out on this problem. Have you taken? So I'll start the screen sharing. So let us go to the board. Okay. Is board visible now? Okay. So when problems have been given based on equivalent circuit of any transformer, we need to first draw the equivalent circuit mentioning the primary resistance, primary reactance, and secondary resistance and reactance. Okay. So these are the details they have given. You just first draw the diagram. So this is V1 source side and this is V2 load side. So what are the data given? Power rating has been given. Q is equal to 20 kVA. Power rating has been given. V1 is 2000 volts. V2 is 200 volts. Okay. Other than that, they have given him winding equivalent circuit of transformer. So R1 has been given as 2.5 ohms. X1 is given as 4.8 ohms. R2 is given as 0.01 ohms, and X2 is given as 0.018 ohms. Whenever problem is given based on equivalent circuit of transformer, you have to put that in the diagram. Okay. So they have told you to find out. First one they have told you to find out R01. Equivalent impedance referred to primary. So equivalent resistance referred to primary. In case if it is asked the equivalent resistance referred to secondary, it should be mentioned as R02. Okay. That is also they have asked. I just explain what it is. Okay. And second one, they told us to find out equivalent impedance referred to primary. Equivalent resistance referred to primary, equivalent impedance referred to primary. Third one, equivalent resistance referred to secondary, equivalent reactance referred to secondary, equivalent impedance referred to secondary. So all the details are referred to secondary side of the transformer. And finally, core loss. Sorry, copper loss of the transformer. Okay. So we will derive that. Initially, we'll go one by one. So I take this problem. The reason is, in this problem we have calculated all the details of the equivalent circuit of the transformer. So R1 value and R2 value has been given. X1 and X2 values has been given. With the help of this, we are finding out the total equivalent circuit parameters of a transformer. So okay, that is the reason I took this problem. So if you understand this problem clearly, you can do any problem based on equivalent circuit of a transformer. Okay. So R01 is given. If you remember, you can write the equation, or else you look at the board. R01 is R1. So when it is referred to primary, keep the primary value as it is R1 plus R2 dash. R2 dash stands for secondary resistance referred to primary. Okay. R1 is primary resistance, same value. R2 dash is secondary resistance referred to primary. Okay. So there is a formula for R2 dash. The formula is R2 divided by K square. R2 divided by K square. Okay. So we have to find out the K value. How to find out K value? What is K? Transformation ratio. That is what we saw in the last class, yesterday's class. K value can be found from these two. Okay. V1 value and V2 values has been given. So write it here itself. K equal to V2 divided by V1, which is 200 divided by 2000. What is the value? We will get 0.0. 0.1 or 0.0?
0.1, sir.
Yes, very good. So put that in this equation. So we know the value of R1, we know the value of R2, and K value has been defined. Okay, so put these values here. So R01 must be R1, which is 2.5, plus R2, which is 0.01, divided by 0.1 square. So 0.1 square is 0.01. Okay, so these two will get cancelled and it will be 1. Okay, 2.5 plus 1 is 3.5. Okay, so first subdivision we have calculated the right answer. Okay, R01 equal to 3.5 ohms. Next one we will find out the impedance. To find out the impedance, we require two details. One is R01 and X01. Okay, this is the answer, isn't it? So impedance is usually given as Z equal to square root of R square plus X square. Here we are calculating the impedance referred to primary. So the notation is given as this, R01 plus X01. Okay. So which is, we have calculated R01 value, but X01 value we don't. We need to calculate that first. X01 is equal to the same equation, X1 plus X2 dash. Okay, how to find out x2 dash is x1 plus x2 divided by k square. Okay, so substitute that value x1. What is x1? x1 is 4.8 plus x2 is 0.018. 0.018 divided by k square, which is 0.1 whole square. K value we calculated from the voltage values. Okay. Again, this will become 0.01 in the denominator. So what will happen is, it will become 1.8, 4.8 plus 1.8. Okay. So the total value is 6.6 ohms. X naught 1 is 6.6 ohms. Okay. So put this value in impedance equation. Z naught 1 is equal to square root of, what is the value of R naught 1? I forgot. Just R naught 1 is 3.5. 3.5 whole square plus 6.6 whole square. Okay, someone tell me the answer. Z naught 1 is equal to
7.47, sir.
7.47, very good. That is the answer. 7.47 ohms. Okay. So in the similar manner, you need to calculate. So this, with this, the second subdivision is over. Okay. The third subdivision, they have asked all the details. R naught 2, X naught 2, and Z naught 2. Okay. I am going to write just the equation for this, and you need to find out the answer and tell me. Okay. I will call out the names. Those members has to answer for this question. Okay. I will write the equation. I'll write the equation, but you have to simply apply the values of that equation and tell me the answer. So R naught 2 is R1 dash plus R2. R1 dash is R1 into K square plus R2. Similarly, X naught 2 is X1 dash plus X2, which is X1 into K square plus X2. Z naught 2 is square root of R naught 2 plus X naught 2 square. Okay. When it is referred to secondary, the K will be in numerator. When it is referred to secondary, the primary, it was in denominator, but here it is in the numerator. Okay, it is in the product. Okay, you find out the answers and tell me what is R naught 2. First, first I want the answer for R1 dash. R1 dash. Ashwin, can you unmute yourself?
Yes, sir.
What is the answer for R1 dash? R1 dash. Many students are leaving, they are asking questions. I could see some names are leaving the meet. Suganand is always leading the answers. Okay, Ashwin, the answer has been given in the chat box. Please look at it. R1 dash is 0.035. Okay, what is X0 2? So I have written the answers directly. What you need to do is simply put the values here and substitute the values here and find out the answer. Okay, the final answer is this. X0 2 is equal to 0.066 and Z0 2 is 0.077 ohms. Don't forget the unit. Okay, so this is the answer for third subdivision. We have find out R0 2 value, X0 2 value and Z0 2 value. So all the details have been calculated. Okay, I have written the formula and answer. You need to just simply substitute the values. Okay. So in the last step, we have to do this. The last step is we have to calculate the total copper loss. So what is the formula for copper loss? PCU is I1 square into R01. I1 square into R01. Here current, there is no detail has been given about current. Okay, so we need to calculate the copper loss or full load value. So what is the formula for finding out I1 is kVA rating divided by V1. Okay, so what is the kVA rating of the transformer? Given data, erased it. 20 kVA. So which is kVA rating of the transformer is 20 into 10 power 3. V1 value is 2000. So this will cancel. 200 divided by 2, which is 100 amperes. Sorry, 10 amperes, isn't it? Yes, 10 amperes. Okay, I1 value is 10 amperes. So total copper loss PCU is equal to 10 square. What is the R01 value? What we found is 3.5. So which should be 350 watts. Okay, do you understand this? So all these equations have been derived in open circuit and short circuit while conducting teaching about open circuit and short circuit. Okay, so if you have any doubt in the problem and share the video, please go through that. In IL, you can call me. Okay. So it is the time for asking some questions. I'll give you a work. Please do this. Look at the screen. I have shown the slide. Example 31. The primary and secondary winding resistance of a 40 kVA 6600 volts per 250 volts single phase transformer are 10 ohms and 0.02 ohms. Okay, they have given primary and secondary winding resistances. And equivalent leakage reactance referred to primary. X01 value has been given. For resistance, R1 and R2 values has been given. In the reactance side, they have given X01 value. Okay, and they are telling you to find out the full load regulation of different power factors. Okay, at what is the regulation at unity power factor? What is the regulation at 0.8 lagging power factor, and the regulation at 0.8 leading power factor? Okay, so we derived an equation for regulation, voltage regulation of a transformer. You will get an equation like called I1 into something. That equation, I'll show you the equation and you know that equation. Okay, so just by looking at this equation, you can directly substitute all the values. The detail which are missing is for this voltage regulation equation, R1 and R2 values has been given. You need to find out R01. Likewise, what we did in the problem, in the last problem, the values of R1, R2 was given. We calculated R01. Okay. In the same manner, you have to find out R01 out of these two values. To find out K value, use the voltage ratio 6600 and 250. Okay, so you will get K value from here, R1, R2 here, so you will get R01 easily. So putting that in this equation, you will get the voltage regulation of the transformer. Okay, it is very simple, and I will derive in the next class also. And today at 4th session, we will be having tutor ward meeting. Tutors, myself and Vidya ma'am will be presenting. If you have any doubts and if you have want to give any feedback about courses, other courses also, you can give. Okay, please be ready for that. Thanks for attending the session. See you in the next class. Please take a screenshot of this problem and I want you to work out on this.